So this particular file is doing one thing basically. It's taking that JSON file, which is the instances validation dataset, instances validation 2017 for Coco, and it is giving you, it is returning a CSV file, basically taking all the input from that particular file and returning a CSV file. Now, while you might want to return the CSV file for something like doing something basic like what we are doing right now, uh, in the long run you might not. You probably just want to pass that data frame through to your other methods, uh, and the methods that it will pass to are written over here in the det2 file. So that is basically the registration methods, and I'm yet to get to writing the registration method. I've still not done that, the register data. But before that, I want to display some functionality from Detectron, because we have not really looked at anything from Detectron right now. So what, even in my GitHub this thing comments for the pull request, I don't necessarily mention much about what is the functionality that we are going to use from Detectron, the registration and all that. So it is just that you will probably end up doing something. So right now it is just in that stage that we will end up doing something with this standard data decks. So what we can look at is why we have taken standard data decks as the structure for this particular, or the data structure for this particular work that we are doing. These are the options when you go to their official documentation. So the chosen option is Detectron's standard data set dictionary, Detectron's standard data set dict, as described below. This will make it work with many other built-in features in Detectron 2, so it's recommended to use it when it's sufficient. So yeah, I found it sufficient, yeah, and I used it a couple of times earlier. Um, so easy to code, easy to understand, and that's the reason we are doing this. So that method, which is basically get standard data dictionary. So this is the one that we'll look at first. So we've seen that CSV. That CSV has given us this format. So the bounding box area, there's another ID which is there. So image integer ID, category ID. Category ID is basically the classes. So because it's the Coco dataset, there's almost like 80 classes over there. Then you have the bounding box for each category. So top left x1, x2, y1, and bottom right y2. Right. So this we will see in more detail now. And then you have the remote URL, the internet, so to say, URL for the particular image. And then you have the image file name, the JPEG extension, and you have the image local path. So where is it saved on my local system, my Ubuntu right now, or maybe it's saved on your server somewhere, wherever you would have downloaded it. So that will be the image local path. Yeah. So what exactly are we doing here? So with this, all this information coming in, we want to move it into a standard dictionary format. And to do that, okay, first we read the CSV. Why am I chunking it? Chunking not because it's a very large CSV or I want to memory optimize or something, but I use this for something else later on, so I'll kind of explain. And then this is where the actual code starts. So you're iterating over the length of that particular um, series, the pandas series, and then you're getting your image name and the ground truth label and your 4 coordinates. So once you got all this information out of this, you read the image, use CV2 to read the image. You get the image channels, height width is what we are using right now. Channels we are not using. You get the bounding box height, bounding box width, X center, Y center. This is the YOLO format. So in case you wanted to do this with YOLO, you probably end up doing this bit. Yeah, from here to here. But let's say we were not to do this. So what I am actually doing is I am also preparing data for YOLO. I am also preparing data for Detectron. So from some of this, I derive the Detectron format or the Coco format, right? So here, then I take the float center, float y center, um, and min x, min y. Once this is done, I have the Cocoa height, Cocoa width. I start creating the Cocoa standard data dictionary. So this Cocoa standard data dictionary will be for one particular image, right? And within that image, what we will have is we will have a Cocoa bounding box, and the bounding box will go into another sub dictionary, so to say, or nested dictionary within that, called the annotation. Within this annotation, we will have the annotation ID, and this is all Cocoa format. You can read this in Detectron's structures. Uh, they call it the structures, probably the data structures is what is meant by this. And then you have the bounding box, which we created over here. This bounding box, it goes in as a key value over here to the bounding box key. Bounding box mode, the area, the category ID is crowd is usually supposed to be 0 in case if this annotation belongs to a object, to a foreground object, is not really the crowd, then you can keep this as 0. But you can avoid this. Even if you don't use this, it'll still work. And this is segmentation for semantic segmentation, but we are not doing semantic segmentation. We are just doing object detection, so we will ignore this for now. And this is where you append your annotation. Your single annotation gets appended into this list, which again goes into your standard dictionary, and this is the final format that you get to see. And for now, I think I've commented this bit out, so while I will run it, okay, so yeah, I can uncomment it, doesn't matter. So this is what we are running. So that is one method. Then the second thing is we will use this standard data dictionary, list of standard data dictionaries, and we'll register the data set. So this I have still not done. This will be done. So the input arg will be this. So this will be the input arg. And then again, this is something else which is still not done. Then coming to getting images for test. So now what we can do is we can pick up some of these images that have basically got written into this dictionary, or we can even pick them up from the this CSV file which we have. We pick them up and we do some prediction of bounding boxes on them. Now the question is, how do we do a prediction of bounding boxes? We still don't have a trained model. We haven't trained our model. We haven't registered our data set, and we haven't trained our model. So those two steps are pending, which are obviously very critical, but we can still try out, because what Detectron is giving us is that functionality wherein we can merge from a config file, pick out of their model zoo what we want to any model that we want to test, or any model that we want to use as the backbone, and then do something additional to that. Or for transfer learning, if you want to do transfer learning over here, it is quite possible that we can straight away use these weights and not not train the model from scratch, and do additional training. So that additional training and transfer learning and everything I will show later on. But right now I'm just showing this, displaying this very basic functionality of the model zoo. And just by merging this config file from here, from the model zoo, you can pick up these pick up these models. And once you pick up these models, and the first time that you run this code, so right now I already run it a couple of times, so won't happen. But if the first time you run this code, such a pickle file would get downloaded on your system. So 168 MB, and this got downloaded, and this is for this particular model. So let me show you where this is. This is part of the model zoo, model zoo.py. Yeah. And this is the one for, so Cocoa detection, faster RCN R50, so ResNet 50, FPN 3x. I'm sorry, I forget the FPN. And this is the model final. So this is the pickle file that they have, which is the model final, and this is which will get downloaded on your system if you run exactly the same code. And okay, then the model ROI heads score thresh test. This I will again explain in detail later. But what that basically means is when we print the config and when we look at the model config, we will have ROI heads for our object detection, and within that there will be a score thresh test, a threshold score which is put for testing, which is at 70%. So this will be 70%. Then again, moving the model to device CUDA. So the model will move to the GPU if you have a GPU. So in my case, I do have a GPU. So this will work out. And then there's a default predictor which is there. And this default predictor will use any config that you provide to it. So right now we are providing it this config itself, and we've not really added anything to this config. When we do the actual training, when we do the actual evaluation, when we do the COCO evaluation and everything going ahead, we will add to this particular config, and that time also we will get something similar. So the default predictor remains the same, but the config that you pass to it changes. You add to the config basically. So right now with this default predictor and this particular config, what we will end up doing it, this we've already seen. So we've already seen this. I'll collapse this. This one also I'll collapse for now. So with this entire thing set up and that default predictor, we will pass it a test image. So we will pass it any of these images that we've got saved on our system, which is the COCO validation data set. And once we pass it that image will get passed again to a visualizer, or rather a default predictor created. This particular object created will get passed to the visualizer, and the visualizer will then do its job, and it will it will allow you to uh, put the predicted bounding boxes onto that image. Once you put the predicted bounding boxes onto that image, so this is where that thing is happening, and I'll just explain what is this in the middle. I'll come back to this. So over here on line 238, when we put the predicted bounding boxes on that particular image, it will give you those bounding boxes coming out of this instances. And what exactly this instances is, let me explain over here. So when we have that default predictor created, within that there will be instances. So that instances will hold your entire information about the prediction that has happened on that particular image. So what all information will it have? It will have predicted classes, it will have predicted scores, and all of this we will see right now, or rather I can even show you before we run the code here. So if we were to look at the predicted classes, the predicted classes in the raw format come out like this. They come out as a tensor, in which now in this particular tensor there are 4 classes which have got predicted. The first value is 0, the class value. The second value is 16, then 1 and 13. So 4 classes got predicted. And similarly, these are the scores. These are confidence scores. So for class 0, our model is confident that that particular instance, that particular object that it is identified, it is 99% sure that it belongs to the class 0. And then there is one of class 16 which it says 98% I am confident that it is class 16, and similarly 94% and 92%. Right, so that same again, those same scores are coming here. For in place of the tensor, we converted this entire thing into lists, so that we can then further move it into some kind of tabular data, and maybe do various other things with it, which we'll come to later on. So that will come to later on. And over here, it just says tensor and it says CUDA 0. So CUDA 0 means GPU 0. I just have one GPU on this particular system of mine, so it is saying CUDA 0. Let's say if we were to run this code on a system which has got around say 4 GPUs, 5 GPUs, 6 GPUs, whatever, then you can be running this code in parallel. And when you run it in parallel, certain tensors will come out saying CUDA 0, certain will come out saying CUDA 1, CUDA 2. So yeah, so whenever it says that, that particular tensor is being that time stored in the memory of that particular GPU. Okay, so now this is how it will look like, and these are various images. So different images having different number of instances of objects identified. So this image has it has been run thrice and it's got so many objects identified. So these are image numbers basically over here. Like it says image file local path. Yeah. So this is what the instances is all about. And over here, before you draw the instances, it moves that instances to CPU. So for visualization, it is moving it to CPU from the GPU. So that is what this code is doing. And then you just go ahead and save it into this one particular directory that I've created, and gives you a timestamp. Also gives you the name of that particular image, and saves it in a PNG format. So one second, I'll come to that.